we discussed some of the applications of Bernoulli's equation and its principle, and also the utilization of the various components that occur in Bernoulli's equation. As we have discussed already, the equation comprises three main things: the pressure, the velocity, the height, and also density if it is not constant. So we will continue discussions and some of the applications just to familiarize you with how do we interpret different phenomena and different things that where this equation is applied, the principle is applied. And here is another equation, another example. We are doing some of the exercises utilizing this equation and finding the phenomena. I discussed with you in one of our discussions that blood flow in arteries is an important phenomena for researchers, mathematicians, doctors, engineers, and so on, because of the heart problem and the blood flow mechanism that is occurring these days and that is causing problems. So therefore, even in modern textbooks, the assignment, the exercises that they do give some applications regarding blood flow mechanism. Of course, it does not involve too complicated systems. It does not need a lot of biological or medical information. We will restrict ourselves only to simple mathematical application of Bernoulli's equation, just to show that at some stage the doctors or the engineers who are developing certain instrumentation and the doctors who are studying the subject, they need to know this kind of thing. And this is illustrated by this example that we are considering here. So there is a small question, simple question, that a large artery in a body has an inner radius of 4 into 10 to the power minus 3 meters. The blood flows through this artery at the rate of 1 into 10 to the power minus 6 meter cube per second. The blood has a viscosity of 2.084 into 10 to power minus 3 Pascal second, which is the same as poise, and a density of 1.06 into 10 to power 3 kilogram per meter cube. And from this information that has been given in this exercise, we are asked to calculate the average blood velocity in the artery, because at times it's important to know how the blood is flowing. We are always, every day we are talking about blood pressure, things related to that, but also blood pressure is related to velocity and also the pumping of the heart and so on. So this problem that we are going to discuss is a very simple problem in nature, but it is related to somehow the real problems. The pressure drop in a 0.1 meter segment of the artery. So they want to know how much pressure will drop in this much distance or section of the artery. The Reynolds number for that blood flow. All these things depict and reflect the blood flow mechanism. It helps the doctors or whoever is looking at the problem to understand the situation properly. And the second part of this question wants us to look for, briefly discuss each of the following: the velocity profile across the artery, and if we give a diagram, they say it will be helpful. So we can draw a diagram of the velocity profile that may be taking place in the artery. the pressure drop along the segment of the artery, and the significance of the value of the Reynolds number. So, this is an extension of the first three parts of the question that were given. There they need to calculate them, and in the second part, they say briefly discuss their significance. So that is the question. So, as always, first we try to look at the given data. The given data in the question is that the radius is given to us of the artery is 4 into 10 to power minus 3 meters. The volume flow rate is given as 10 to the power minus 6 meter cube per second. Viscosity of the blood, eta, is given to be as 2.084 into 10 to power minus 3. Of course, if we need, we can write it in decimals also. And the unit here, again, they are using Pascal second. For viscosity, sometimes we use poise as the units, but that is not very common, and instead Pascal seconds are used. Density of blood is 1.06 into 10 to power minus 3 kilogram per meter cube. So this is the given data, and we use this data to compute our calculations. First, we see that by conservation of mass, we have not derived yet the equation of continuity in the differential form, but broadly this is from conservation of mass. As we discussed already, that mass cannot be created or destroyed, it is retained. And in this case, we need to know that the quantity of the blood flow with the area, cross-sectional area, times the velocity with which the fluid is moving. And in the fluid happen to be the blood. So, the area A is equal to pi r square. For a circle, what happens is that artery may not be cylindrical 100%. But for the sake of calculation, and this is supposed to be a reasonable approximation, and arteries in the human or any living body's mechanism is treated as a cylindrical body. So the area is pi r square for a circle, and since it is circular, therefore the area, the cross-sectional area will be pi r square. So when we want to calculate and know how much is the quantity of fluid that is flowing, and we want to substitute in this quantity Q is equal to A into V, then A is pi r square. The given numbers are here. When we calculate them, of course pi is 22 by 7, and we write that for pi. When we make our computations, we arrived at the result as 5.03 into 10 to power minus 5 meter square. The velocity from here, we can calculate, it will be Q over A, and since Q is given to us, we substitute this value of A here that we have just calculated in the above line, and therefore the velocity V turns to be V is equal to 1.99 into 10 to power minus 2 meters per second. So that is the first part, that they want us to calculate the average blood velocity, and here we have calculated the velocity.